All right, so if you looked at the calendar that I did, we have this test on chapter 14, and then we only have one more, and then that's it. Then we start reviewing for the AP exam. They have chosen the second date, which if you look at the calendar, I have it in there. So look at the new calendar I posted. Okay, so chapter 14, equilibrium. Something that we have never done before. I'm going to look at this equation right here. Oops. Sorry. And I'm going to look at it on the other page. But it's pretty simple. So we have this color. So we have H2 gas plus I2 gas makes 2 HI gas. So we have a pretty simple reaction here. You have a hydrogen molecule, you have an iodine, which would be bigger, and then over here you get 2 HIs. Pretty straightforward. All right, now why is this new? Well, here's what makes this new. What makes this new is as this reaction happens, so it's going from right to left, hydrogens are coming together and they're making HIs as we would normally see happen. But here's the weird part. These start to collide and then start to form H2s and I2s. So this reaction actually starts going back in the other direction too. So we have the forward reaction, which is what that's referred to as, the forward reaction. Now we have the reverse reaction as well. So in the beginning, you have hydrogens reacting with iodines, forming HIs. Eventually, enough HI builds up and the reaction starts to go the other way. You don't stop making HI though. So H2 and I2 are still producing 2 HIs, but the 2 HIs start to decompose, react and go back into H2 and I2s. I used to describe this as, having an annoying little brother. You're doing the laundry, you're putting socks together and you're putting them in a basket. So H2 and I2s are coming together and making HIs, but then your annoying little brother comes over and he starts taking the socks apart and putting them back in the basket. So you are making HI and then HI is making H2 and I2. All right, now how does that complicate things? Well, here's how it complicates things. What we have based, or what I have based for you, really your last 2 years of your life dealing with chemistry was stoichiometry. And I showed you all year long how to get really good at stoichiometry to be able to calculate pretty much anything you come across, with the exception of equilibrium. So stoichiometry doesn't work anymore. Because if we said, 100 grams of this reacts, how much of that are you going to make? That's stoichiometry. Well, you're not going to make that much because we just said this thing starts to go back in the other direction. So we have to introduce a new concept and a new topic. So that's what equilibrium is all about. All right, so let's read through this together and we'll get to what we need to learn for this. Okay, so when initially looking at a reaction, we often assume, and the term is, it goes to completion. That's actually what the phrase that's used is. Does the reaction go to completion? That would mean stoichiometry works because 100% of it reacts. That is to say that as much product is formed as it allowed by the reactants that are given, stoichiometry. In reality, though, most reactions do not. Notice the phrase there, most. I haven't even mentioned this. You've been in chemistry for almost 2 years, year and a half, but most reactions are actually equilibrium. It's just that some of them, they're usually so close to 100% that we ignore them, at least in first year chemistry. Now we have to start dealing with these as they're not 100%. All right, so in reality, most reactions do not go to completion. Instead, they reach a point of minimum free energy that is a mixture of reactants and products. It's called the equilibrium point. So you're going to get to this point where the reaction looks like it's no longer proceeding. In other words, the products concentration are no longer changing, the reactants are no longer changing, but the reaction is still occurring. It's just occurring in both directions. All right, so at equilibrium, the reaction has not stopped, but rather the forward reaction and the back reaction, or the reverse reaction, are occurring at the same rate. So there's no net change in the concentration of the reactants and the products. Therefore, it is referred to as a dynamic equilibrium. This does not mean, though, that the reactants in the products have equal concentrations. Only that the forward rate of the reaction is equal to the reverse, such that the concentrations are no longer changing. Not equal, but constant. I'm going to revisit that. All right, so we just learned about the speed or the kinetics of a chemical reaction. How concentration changes affect the rate of the reaction. Generally, an increase in the concentration will increase the rate of the reaction, first order, second order. And a decrease in concentration will slow the reaction down, decrease the rate of the reaction, except zero, because remember, zero doesn't affect the rate. All right, so if we start with only H2 and I2 in a container, what happens? Well, what happens is, as I described, the reaction is going to proceed in the beginning only from left to right. Only from left to right. It can't go from right to left because there is no HI yet. So initially, no HI. You can see that in the picture down here. We just have H2s and we just have I2s. So then they say after some time, after more time, after more time. So the reaction starts to go in this direction. Well, once it gets here, now you have some products. So now it starts to go in both directions. And then eventually we get to the point where the concentration is no longer changing. Look at the graph. So these graphs should look familiar. We're graphing concentration versus time. Concentration versus time before was a way to determine the rate, or the rate law, first order, second order, zero order. So you can see H2 and I2 are matching what we would have seen. So they're starting at some concentration and they're gradually decreasing. Now what we saw before was they would have gradually go all the way to zero. All right, so now they're not going all the way to zero, but they are going to, so concentration to a constant concentration. So at this point right here, dynamic equilibrium is reached at a certain amount of time and the concentrations no longer change. So then why do we teach that some reactions go to completion? Well, for many reactions, it's very nearly the case. If only one in a few trillion molecules don't react, it's not worth talking about the equilibrium. But for many chemical processes, even a small amount of the reactants are of interest. And thus, even at these extremes, we're often interested in the equilibrium concentrations. So not stoichiometry again, but equilibrium. All right, so we're going to find something called the equilibrium constant, and it is a capital K. We're going to make our way through the rest of the year dealing with different Ks. In the beginning here, it's K dealing with molarity, and it's K dealing with atmospheres if it's a gas. We're going to go into Ka for acids and Kb for bases and Kw for water next. And then we start adding some other Ks, something called a KSP. So there'll be some other Ks. All right, but they're all found the same way. So at equilibrium, there is a relationship, as we just said, between the concentration or the partial pressure of the products and the reactants. So there's a relationship between, or a ratio between the reactants and the products. We will see that these are the concentrations that minimize the total free energy. In other words, they lower the energy, and it's kind of back to that idea of if you put a ball in the middle of the ramp, it rolls downhill because down here it has lower energy. So that same idea, Gibbs free energy, delta G, if you remember. All right, so but for now, we're going to simply say that that's possible. So we're now saying that it's at the lower energy. This is where equilibrium is reached. For different types of chemical species, the free energy at equilibrium is related to different standard states. As such, we end up with different types of equilibrium constants. As I said, the two we're going to do today are called Kc for concentration and molarity, and Kp for the pressure of a gas, the partial pressure of a gas, and it's actually in atmospheres generally. All right, so the equilibrium constant then is a ratio of the activities of the products to the reactants. The activities of each chemical species is raised to the power of its stoichiometric coefficient in a balanced reaction. Therefore, to be interpreted, an equilibrium constant must also be accompanied, or always will be accompanied, by a balanced equation. So you're going to get a balanced equation. We're going to look at the coefficients in the balanced equation, and those are going to be raised to the power. So they become exponents, as you'll see on the next page. So look at this example. So a generic reaction of lowercase a, so that would be the coefficient in front, you know, a number, 2, 3, whatever. And that goes over here on the bottom. So if we evaluate what we have, you notice we have C and D on the top. So it goes products on the top over the reactants on the bottom. Products, C and D, over the reactants. This is called a law of mass action, the law of mass action. And what we're writing here is something called an equilibrium expression. Equilibrium expression. So if I scroll down a little bit more. So in our example here, again, A, B, B, C, C, D, D, instead of a KC, so this would be KC. Again, the C stands for concentration, and the concentration unit that you must use is molarity, which we already saw in our rate laws. Anytime you see a number or a formula in brackets like that, that means molarity. Down here, we're doing a KP, where we do KP then stands for the pressure. So the P is the pressure, and it is measured in atmosphere. So the partial pressure of each gas. When you're going from the KC expression, which you use brackets, they're very specific about the way you write the KP on the AP's chemistry exam. Meaning, if you use brackets, they mark it wrong because they want to make the distinction between a KC and a KP and that they're different. So if you write the K like that, they're gonna mark it wrong. It's okay to use parentheses, but I would recommend nothing like I have there. And you'll see as we do a few of these. All right, so let's write the KC and the KP. So the only difference between the two is, besides the ones in molarity and ones in atmospheres, when you write a KP, you only do the gases. Only the gases. But I made this one easy, they're all gases. So the KC, so again, they're called expressions, equilibrium expression. You put the products raised to their exponents on top, and they're multiplied. Here they're added, but here they're multiplied. Divided by the reactants, again, raised to their power. So then when we write the KP, we don't use brackets, it would be marked wrong. Same thing, products, but now it's a partial pressure. So the pressure of NO2 raised to the 4th power, and I like to put the X in there, just like I had in my example. I always do that. Partial pressure of O2 to the 1st over the partial pressure of N2O5 squared. All right, so hit pause for a second and try the second one. All right, so once again, we're writing equilibrium expression. That's what this is called, an equilibrium expression. So this would be O2 to the 5th, C3H8. I just did it upside down, sorry. CO2 to the 3rd, H2O to the 4th. So the products on top and the reactants on the bottom, and the coefficients become exponents. When you do the KP, you only do gases, they're all gases, and no brackets. All right, so what are we doing with K? So we're going to do some things to K. Today we're going to look at what happens when you manipulate the equations. If you reverse it or you have to multiply it by a coefficient like we did with Hess's law, it's different when you're doing K values. The equilibrium constant is related to the concentration or partial pressures of the products divided by the reactants. So if the equilibrium constant is larger than 1, so if K is greater than 1, K is greater than 1. I don't know which one math teachers like. There will be more products at equilibrium. Because if products over reactants, if it's greater than 1, you're multiplying by a bigger number than you're dividing by. If it is the other way around, if it is less than 1, now you have more reactants than you do products. So you'd have more reactants at equilibrium. So it's a qualitative idea, as the concentrations are often raised to power. So don't forget, you do have to square or, fifth root or fourth, some of these. And so you're not really looking at the exact amount, but you are saying whether you have more of one compared to the other. Nonetheless, it is, again, you'll see as we move forward, a very valuable idea that you're going to use. So the phrase that we use is called favors. So if it's greater than one, we say it favors the products, or the products are favored. And if it's less than one, we say the reactants are favored. Now, you can have huge K values, times 10 to the 19th, even bigger, and really tiny ones, particularly when you're doing solubility. So what we would say then, look how much greater than that is than one. So that means you have so much products that you would say essentially that this thing goes to completion. Now this is where, if you remember that equation, there's that K value. And if the K value is huge, that means the reaction was spontaneous. Remember, because you're gonna have lots of product. It is gonna happen. You'd have a negative delta G. But with a tiny number like this, that means products over the reactants. A really tiny number like times 10 to the minus 31st, that means you have mostly reactants and very little product. Very little product. So we say that this reaction, essentially nothing happens. Very little products. All right, so when the equilibrium constant is fixed, there's an infinite number of combinations of concentrations that will give you the same ratio. However, at equilibrium, we will have the same ratio as the K value. So the K value is always going to be the same. So the equilibrium constant for the reaction, A is in equilibrium with B, and the K is equal to 10. Now it says a reaction mixture initially contains 1.1 molar of this and 0 molar of that. Which of the statements is true at equilibrium? All right, so we're not at equilibrium. We're initial. And you're going to see we're going to make something called an ice chart tomorrow, an ice chart. And ice stands for the initial concentration, the change in concentration, so IC, and then the equilibrium concentrations. Well, this is saying the initial concentration. Now it says, which of the following statements is true? A reaction mixture will contain 1 molar of A and 0.1 of B. The reaction mixture will contain 0.1 of A and 1 of B, or they're going to be equal. Maybe they're both, well, they would have to be equal to 10. So that's not going to be possible. Can't be equal. Because the K expression is equal to the concentration of B over the concentration of A raised to the first power for both. Because again, balanced equation. Now we know K is equal to 10. So if we're at equilibrium and A is 1, so if this one's true and B is 0.1, that would be equal to 0.1 for B divided by 1 for A, which is 0.1, which is not 10. So this one's not possible because at equilibrium, the K value would not be 10. What about the second one? So now we're saying B is 1 and A is 0.1. So 10 divided by 0.1, that's the same as 10 divided by 1/10. 1 divided by 1/10, which is 10. Yeah, that one does give us the right concentration, and then there's no values where it would be equal. All right, so often we have an equilibrium constant for a particular reaction, but we would like to know it for a different reaction. In the same way that we can add or subtract reactants from one another, we can manipulate equilibrium constants. So if you reverse an equation, now different than Hess's law. Remember, Hess's law dealt with delta H. And delta H was, if you're going this way and you have a negative delta H, that means it's exothermic. If you go the other way, that means it's a positive delta H and you're endothermic. So with Hess's law, all you did was change the sign if you reversed it. Well, this is not the case anymore because we're dealing with, physical concentrations, not heat. All right, so if you reverse the reaction, you take the inverse of the equilibrium constant, or you flip it, you inverse it. Why? Well, let's do the example we just did. A was in equilibrium with B, so the K expression is the concentration of B over the concentration of A. If I reverse this reaction, Now A is the product and B is the reactant. So notice what happened. So we reverse the reaction and we flip the equilibrium constant. So A plus 2B is an equilibrium of 3C. So products over reactants, there's the forward reaction. If you reverse the reaction, you can see now C is now the reactants. So whatever the K was, you just inverse. So 1 over whatever K of the original was, inverse. If you multiply, well, in Hess's law, when you multiplied, you multiplied. Now it's not the case because whatever is in front, coefficients, remember, become exponents. So if I'm multiplying everything here times 2, now the coefficient is 2, 4, and 6. And so the exponents are 2, 4, and 6. So if you multiply the coefficients by a factor, you raise the equilibrium constant to that factor. So you raise it to that power. So if I do multiply them all times 2, whatever the original K was, then I have to square. And then the last part is when doing Hess's law, if you remember, it was the sum total. So the sum of each equation. That's not the case here now. It's the product. So you multiply them, and you can figure out the algebra if you want to. But you don't add, instead you multiply. So it's the product, not the sum. Product and not the sum. All right, so the reaction A now yields 2B, different, has an equilibrium constant, so K is equal to 0.01. What is the equilibrium constant for the reaction of B? So B, so we got to reverse the reaction. So remember, reverse, you do 1 over K. And we also need a 2 in front, so we have to multiply by 2. And so we're going to do 1 over K to the second power, because we're reversing it and we are multiplying by 2. So we inverse and we raise it to that power. So we have 1 over the K value, which is 0.01 squared. Here's a trick we're going to learn soon, because I have to teach you this to do the multiple choice. So 1 over 100, because that's what this is. So 1 over 100 is 100. 1/100th. And we don't, yes, and now we got to square it. So how are you going to do that? Well, that's really for you to figure out. So I'm going to show you a way to do that where we can figure this out. But for now, since we can use a calculator, just grab your calculator and see what you got. So you can do 1. I don't know if you can see my calculator. I don't think I shared it. And it will give you the correct answer. So we're reversing it. So it's the inverse, even if you do it in parts. So do 1 divided by 0.01. So that gives us 100. And then we are, oh, I'm doing squared. We should be taking half. You're probably yelling at me. Not squared. So we're now doing to the half. So that would be 100 then raised to the 1/2 power, which is the same as square root, right? So you probably figured it out a while ago. There you go. Second example, consider the chemical equation. So now once again, we're looking at this one compared to this one. Here we are multiplying by 1/2 again. So we're taking 1/2. Actually, and we're reversing it again. So the N2 is going to the other side, and we are multiplying by 1/2. So we're going to do 1 over 5.6 times 10 to the 5th. There's the inverse part. And then whatever we get for that answer, we're going to raise to the 1/2 power. Or you could do it all at once. Your choice. Again, you know how to do algebra. 1 divided by 5.6 times 10 to the 5th. And then raise that to the 1/2 power. So we get 0.0013 as the K value. So now which is, a value less than 1, reactants are favored, value greater than 1, products are favored. So some more practice. So I would hit pause and try these two and see what you think. All right, so hit pause. I'm gonna do them below. All right, so here goes. So consider this first reaction. So we have to get, again, we're reversing it. It's on the wrong side. So 1 over K. And now we're multiplying it times 2. So this time we are squaring it. So it would be 1 over 2.2 times 10 to the 6th squared. So 2.2 times 10 to the 6th squared. And then 1 divided by that, or the inverse. So 2.07 times 10 to the minus 13. So we reverse that. Once again, less than 1, reactants are favored. Greater than 1, products are favored because we reversed it. So the reactants became the products. All right, so predict the equilibrium constant for the first reaction shown here, given the equilibrium constant for the second and third. So we want to end up with this reaction. And remember, you don't add. It's going to be whatever we get for K2 times whatever we get for K3 equals K1. So that's on the right side, so we don't have to do anything to that. And the water and the CO, you can see, are on the, well, not the CO, but the water's on the wrong side. So we're going to reverse this one. We're going to leave this one the way it is. Let me rewrite it just to show you everything cancels like it's supposed to. So there's reversing the first one. So we're going to do 1 over 1 times 10 to the 5th. And the second one, we're leaving the way it is, and we're not multiplying it times anything. And so that one is 1.4 times 10 to the 7th. So this is going to be 1 times 10 to the minus 5, because we're inversing that, times 1.4 times 10 to the 7th. And that's going to give us 1.4 times 10 to the 2nd. All right. Last page. All right, we got to add something because not everything is included in an equilibrium expression. So many reactions contain pure solids and pure liquids. How do you know? Well, because it'll say an S or an L. Sometimes you'll see a CR instead of S for crystalline solid. And they are never included in equilibrium expressions. So when we do the Kc, everything's molarity. And when we do Kp, everything's partial pressures and atmospheres, but you do not include pure liquids or pure solids in either one. And the reason is because their molarities are constant. I'll run through the math quick, but how do we know it's constant? Well, consider water. Liquid water, this right here is not going to be included in the equilibrium expression. And so there's the Kc that we get. So you see the products over the reactant. Coefficients became exponents, but they were all ones, but we left off the liquid water. Same with this one, we're leaving off the carbon, so there's that. Now, why are we leaving those off? So consider water is a molar mass. We know that its molar mass is 18 grams per mole, and it has a density of 1 gram per milliliter. So if we wanted to end up with molarity, we need moles on the top. So we're going to divide by 18 grams per mole, because now we have moles on top. And now I can use the density, which would be 1 gram per milliliter, and then 1,000 milliliters in 1 liter. Milliliters and grams cancel, and you can see we get moles per liter, the molarity. Well, it's always a molar mass of 1, and it's always a density of 1 at a particular temperature. And so the molarity never changes. So really, we are including them in the rate constant. It's just included in the value, and then the substance itself is left out. So any liquids or solids are always omitted. So let's write the Kc and the Kp for both of these. So try them again, hit pause. There's only 2, and then try that bottom one. And then on the next page, this is the homework assignment. I do have an assignment there in Google Classroom. So try those 8 problems from our textbook. We'll try to include those all as we move along in this unit. All right, so the answers. So the Kc. So the Kc is, we have to include the product, CO2. We're not including that, it's a solid, over the reactant. 1 and 1 for the coefficient. And then the Kp expression, remember, you only do gases. Oh, I included the solid there, oops. So actually, this should have been just CO2. So the Kc is just CO2. So just, I didn't notice that was a solid too. The Kp then is just carbon dioxide. Again, and not including the solids. And this one we have a liquid, three gases. So the Kc expression is Cl2 squared, HCl to the fourth, and O2. The Kp is Cl2 squared over HCl to the fourth times O2. Remember, no brackets. So when does the Kp equal the Kc? It would be, you could see where the two are the same. This is a, don't worry about that question, actually. We don't have to know Kp or Kc. I should have got rid of that. But it would, where the, I mean, I guess you could call these two equivalent, but in reality, they're not. So don't worry about that. All right, so like I said, try those and we'll begin with that